So I wanted to make a video about resonance to help. I think this will be good because it'll allow you to come back and rewatch this and then see me do it in real time. You can pause when you need to. Resonance is often a tricky topic for students. You really just need to practice. Practice makes perfect. It's in your best interest to do so because resonance will keep showing up and pushing arrows will keep showing up for the rest of organic chemistry. One thing that often trips students up is how to begin drawing resonance structures when their starting molecule is neutral. So we're going to do an example like that. So this structure right here is one of the resonance structures. It's the best resonance structure because all atoms have a full octet and they're all neutral. But there are other resonance structures. When I want to start and I have a neutral molecule, I'm going to look for a carbon heteroatom double bond. In this case, I just have one, that carbonyl oxygen bond right there. So I can take pi electrons here, push them up onto the oxygen as a lone pair. If I do that, I get this structure. So I've got a positive charge on my carbon. It lost electrons when those pi electrons moved up onto the oxygen. The oxygen gained electrons, so it now has a negative charge. So now there are one of two ways that I can go. I've got an oxygen on the right-hand side next to the positive charge, and I have a pi bond on the left-hand side. I'll do the oxygen first. One of these lone pairs can fold in to make a double bond. My arrow starts at the lone pair of electrons, and it ends in the middle of the bond to show that I am making a new double bond. My oxygen atom now has one less pair of electrons, so the oxygen atom in the chain on the right is going to be positively charged because it lost electrons. The carbon atom is now neutral because it gained electrons. So from here then, I can either redraw this structure right here if I want to, or I can just start from where I am. I can move two pairs of electrons at a time. I can take a pi bond and move them out as a double bond there, and then kick these electrons back onto the oxygen there. I have to move both at the same time, otherwise my oxygen, or my carbon atom, would have 5 bonds, and I'd break the octet rule. So the carbon that was at the bottom of my double bond lost electrons, so it's now positive, and the carbon that was at the top is still neutral because it's still part of the double bond. Now I still have a few more to go. None of these look the same as one another, and now I'm in the benzene ring. Once you're in a benzene ring, you can continue to go all the way around it until you get back to the beginning. That's when you know that you've run out of resonance structures. If we're looking at these, the best resonance structure would be this guy right here because it's neutral and it has a full octet for every atom. The second best one would be this one right here. It's neutral overall. I have 2 charged species, but all atoms have a full octet. And then in the case of the other two, they both have a carbon that is deficient in octet and an oxygen with a negative charge, so they are not particularly more or less stable than one another. So I'm going to go to the next slide and continue from where we left off here. What I want to do is take this pi bond and move it over here to make a double bond there. So now I have a double bond there, my positive charge here. These electrons are still here. So again, I'm overall neutral, which I need to be because my starting material was neutral. And then, lastly, I can have these pi bonds come down. And that gives me this last resonance structure. So if I were to take these electrons and move them over there, I would end up with this guy, which is sort of where I began. So I still have my 3 double bonds in the benzene ring. Technically, they've all moved over one. But this resonance shows us overall where the electron density lies in the molecule. So in the overall molecule, it's neutral, but given my resonance structures, I know that I have less electron density at these 3 spots in the benzene ring and more electron density on that oxygen atom right there. Maybe also a little bit less electron density on the carbon atom right there. So this group that's attached to the benzene ring is pulling electron density out of it. And when we show all these resonance structures, it shows us how electron density is spread out through the molecule. Lewis structures are great at showing us how things are put together, but they don't do a great job of showing how electrons are shared. So by drawing various different resonance structures and thinking about a weighted average of those resonance structures, we're able to see the overall electron distribution of the molecule. So let's do one more example here. So I'm going to look for a carbon-oxygen double bond, or a carbon heteroatom double bond. In this case, it is a carbonyl compound. These electrons, the pi electrons, can go up onto the oxygen as a lone pair of electrons. Here's my N. So my oxygen atom is negative because it gained electrons, and my carbon atom is positive because it lost electrons. Adjacent to that positive carbon on either side is either a lone pair of electrons or a pi bond. Either of those are available for participating in resonance. First I'll take this pi bond, so that would fold in and give me a new double bond there. And that would give me this structure here. So now I've got a positive charge on the carbon that lost electrons, and my carbonyl carbon gained electrons, and so it's now neutral. Now again, I could redraw this structure right here if I want to do that, or I can just move 2 pairs of electrons at a time on the structure that I'm on right now. So I could take this lone pair of electrons from the nitrogen and push that down, and I can fold these back over here. If I don't do both, I'm going to have 5 bonds to carbon, and I would be breaking the octet rule, okay, which carbon is not able to do because it does not have accessible d orbitals. So we'll go to the next page to draw that resonance structure out. So now I would have this structure. Now, what students often want to do at this point is involve this pi bond in resonance. But if I look at my nitrogen right now, it has 4 things around it. It has 4 bonds. So because it has 4 bonds, even though it's positively charged, it cannot participate in resonance by having additional electrons put onto it. That would break the octet rule. So this lone pair, or this pi bond on the end there that we labeled, cannot donate electrons to my nitrogen because it already has a full octet. So you can help yourself a lot when you're practicing resonance by counting how many bonds or bonds and lone pairs you have around each atom. If it's a second or first row element, it cannot exceed 8 electrons around it. So some form of 4 groups, either bonds or bonds and lone pairs of electrons.